So we started by implementing this Hilbert fractal on the top edge, which you see here, the right edge, which you see here, and this left edge. Okay. And we went up to the second order iteration of the Hilbert fractal. That means we cut two slots in succession. And of course, we can go on by adding different iteration steps. So we may expect an enhanced bandwidth because the path length of the surface current is actually increasing in that way. But at the same time, this will make the design too complex and implement. And so the fabrication of the particular antenna will become tough. So we need to optimize the benefits of cutting these Hilbert slots and the intricacy and the complexity in the design so that we can have the advantage and the benefit for both these constraints. We even cut an annular slot at the center of this Hilbert patch. I will just show you the front view at the center of this annular patch and showed the importance of cutting this particular annular slot in terms that we seldom get any current at the center of the patch. The current is always limited at the peripheral regions of the patch. That means the edges. So even if we remove some portion from the central region of the patch, that will not affect the results too much. And at the same time, since we are removing portions of a metal itself, the conduction loss which we obtain due to the flow of surface current through a metal only, that is removed. So that also can contribute to increase the efficiency of the designed antenna. Now, taking forward this concept, that means metals do introduce some conduction losses which may deteriorate the radiation characteristics in terms of gain, in terms of efficiency. I mean, obviously, whenever loss is there, that actually reduces the efficiency of the structure. So now the question comes, how can we actually deal with this problem? That means we always want to design an antenna which will give us a decent radiation gain, decent radiation efficiency. So in that case, to achieve that particular target, we need to remove, if not possible, at least reduce the conduction loss. Keeping this view, keeping this design consideration in mind, another entirely new domain of antenna structures came into existence. These are known as the dielectric resonator antennas. Now, dielectric resonator antennas are basically, the focus should be not upon the metallic radiators. Instead, we will use a dielectric block. A dielectric is basically a ceramic material, a semiconductor or a ceramic material, as the principal radiating element. The reason for doing this is, see, if we are using the dielectric as the fundamental radiating element, that dielectric block is devoid of any metal. It is not a metallic structure. It is not a metallic block. It is dielectric. So we are reducing the amount of metallization by a huge extent. Completely, it is devoid of any metal. It is created with a dielectric slab, dielectric block. So the conduction loss can be hugely reduced, and that can have a huge impact on the bandwidth of the antenna and also on the gain and efficiency of the antenna structure. So today, we will design a dielectric block on this already prepared antenna structure and show the result of adding such a block. But before that, I will just simulate this structure to show you the results before adding the dielectric. So for simulation, we need to follow some very important steps in order, which I will be showing you, and you need to follow exactly those steps in the appropriate order which I will be showing you to get the required results in a decent way. So suppose this is the antenna structure which we already have designed. So I will just rotate in plane a bit. See, the waveguide port is also seen like this, okay, which will be serving as the connector, which will serve as the interface between the actual feed line, the antenna, the entry, the gateway of the antenna, and this coaxial cable which will be on this side. So this waveguide port serves as the gateway for that transition region of the antenna. So we have designed this waveguide port. The antenna is also designed. The ground plane is also there on the back side of the substrate. So we are in a position to simulate it. We are in a position to simulate this antenna without adding the dielectric block. So as of now, this is a simple patch antenna. Of course, the patch has been modified by introducing Hilbert, by introducing some annular slots like this. But till now, we have not introduced the concept of dielectric resonators. So let's simulate this. In order to simulate, first, we have to set the tab to the home option like this. Home option we have to select. Next, in the navigation tree, I mean, I should hide all these so as so that you can see the entire navigation tree. See, this is the navigation tree. We have a certain option which is the field monitors. Just observe the cursor. We have a certain option which is the field monitors. See, I have highlighted it. We have to right click on this field monitor. So if you right click on this, the next tab that appears is the new field monitor. So you have to select this new field monitor. Now, what is the meaning of this field monitor? This field monitor actually means that we will be studying some parameters related to the field which is radiated by the antenna. An antenna basically radiates electromagnetic waves. Electromagnetic waves are composed of electric and magnetic fields which are perpendicular to each other. So we are studying some parameters which are related to the fields which is radiated by the antenna, and we will monitor them. We will monitor the parameters. So this can be considered to be the conceptual significance of using this field monitor. So now we select this field monitor. The next pop-up window comes, which is named as monitor. Here under this type option, we have different options like this E field, this H field. E field stands for electric field, H field stands for magnetic field and surface current. Next is far field or RCS. RCS stands for radar cross section, which is a very important parameter of an antenna. So in the session where I will be discussing about the different antenna parameters, I will detail about it. So for the time being, we will be concentrating upon this far field only, not the RCS. Okay, but RCS means radar cross section. And the next one is field source. Now here I want to add one point which you should remember. See, the space around an antenna can be broadly classified into two types. Two subdivisions are there, which are the near field and the far field. Generally, all the antenna measurements, antenna analysis, they are performed in the far field of the antenna. There is a reason behind this also. The reason is, in the far field of an antenna, the angular field distribution is basically independent of the distance from the antenna. That means as you go to the far field, far away from the antenna, if you increase the distance by some amount, the angular field distribution, that means the pattern, radiation pattern of the antenna, that will not change much. And this is a very, very important consideration. This is a very, very important criteria which needs to be satisfied for designing and analyzing any printed monopole antenna. Now see, in these four options, there is only one option which indicates the far field. So we will select that. This far field we will select. We need not select anything with these options, okay, as of now, because we are designing a planar monopole antenna. So we need not select these options. Now, next under specification, two options is there. One is frequency, the other is transient broadband. Now try to think analyzing this antenna in terms of the bandwidth. Now if I ask you a question that whether we want a narrowband antenna or a wideband or a broadband antenna, do we wish to have an antenna which will provide us a very narrow bandwidth or a wide bandwidth? Then what can be our answer? As a very logical response, we always want to work with an antenna which provides us a larger frequency span, or in technical terms, a larger bandwidth. So given a choice, narrowband and a wideband antenna or a broadband antenna, without mentioning some other sophisticated requirements, the obvious automatic choice is broadband or wideband. So here also the same thing we can follow. So we will select transient broadband here. Now when we select this transient broadband, next is the number of samples. See, the number of samples 21, that gets auto selected. Okay. You can increase the number of samples, you can decrease the number of samples, you can keep it as it is. The effect I will tell you. See, when you plot the result, you will basically get a graph. Try to imagine this. You will basically get a graph. If that graph is having less number of points, if that graph is having less number of coordinate points, then the graph will appear to be a step-like structure, okay, in steps. If you increase the number of points, then the steps will they will become gradual. They will not be step-like now, but they will show a gradual transition, which is actually what we want in this case. Okay, a gradual graph is of demand in this type of applications. So for getting a gradually varying graph, what do we need to do? We need to increase the number of points. These points now are known as samples. So the sample value which you see is basically the number of points in the graph which you will be plotting. If you increase the number of samples, then the graph will be more gradual, curvy nature. If you decrease the number of samples, the graph will have a step-like nature. Now I mentioned that increasing the number of samples makes it a bit gradual. It appears that this is only advantageous, but there is a disadvantage also, which can be very well overcome, which can be very well taken care of. The disadvantage is, as you increase the number of samples, the computation time, the time required for simulating the structure, that actually increases. So in an environment where you need the simulation to come very fast, you need the simulation results immediately so that you can process them, there it is advisable to reduce the number of samples. But in some other cases where the quality of the simulation results matter, no matter whatever time they take, you don't have a timeline, a deadline in which you need to submit your results, then it's advisable you increase the number of samples. The computational time will also increase, but doesn't matter. We are not bothered about that computation time. Quality of the simulation, that is what it matters. So again here, there is some optimization which is necessary. So we need to decide whether we can afford some more time for the simulation results to come, or we need to get the simulation results in a very less time, whatever be the quality. That optimization we need to do. So let us take somewhere in between. Let us change this to 30, for example. This accuracy, there is again an option to change this accuracy. See, 3 levels are there: level 3, level 4, level 5. If you increase the level from level 3 to level 5, for example, you will get a more accurate result, and at the same time the computational time will be more. So it is advisable to check level 5, but I will not do that now, because for this difference in the accuracy, for this difference in the quality of the response to be visible to us, to be perceivable to us, we need to operate the structure at a very large frequency. But here we are not doing that. We have defined the frequency from 1 to 10 or 8, whatever, gigahertz. So for observing this difference, we need to select a much higher frequency. If you don't do that, level 3, level 4, level 5 will give you almost the similar kind of result. So if we are getting the similar kind of result from the 3 levels, it is advisable to select level 3 only, because that will save me the computation time at least. Okay, so for this reason, we are selecting level 3. So what have we done? We have selected far field, we have selected transient broadband, we have optimized the number of samples and kept it to be 30, for example, in this case, and the accuracy we have kept to minimum, level 3, because minimum to maximum in this case will not make much of a difference. Okay, so after you make these selections, you have to click on apply, then OK. Now see, there is a bluish green colored box surrounding this antenna. If you see that this box is visible to you, then it means that you are at all eligible to proceed with the simulation. If this blue or bluish green box is not visible to you, then it means some problem is there and you need to modify your structure, modify your simulation definitions so as to process with the simulation. So for us, this is actually coming, so we can process with the simulation. So after this, we just need to start this simulation. The results, actually I have simulated to just check the viability of the results. So this block is coming. This will not come when you simulate for the first time. So I will recalculate. So when you recalculate, this basically will show you the status of the simulation that is being performed, which stage the simulation is there. Some warnings will be there. See, 3 warnings as of now, 3 warnings are there. You need not bother about them because these warnings are taken care by the simulation platform only. These are taken care by the CST only. So we need not be bothered about that. See, what units we have selected, these are displayed here. Number of mesh cells which are being used by this simulation, that is also mentioned here. So just we have to wait for some time for this simulation to complete. So after that, we will proceed with the simulation results. Now, as you can see, the countdown is being shown 121 seconds, something like that. Sometimes it will even come down. Now, if we would have selected the number of samples to be even more, the accuracy to be even more, then this countdown value would have gone higher and we would have needed a much higher time to simulate this. Luckily for us, the time is not that much because we have kept the accuracy level to minimum and the number of samples also low. I will not say too much low, but it is actually low. But that won't hamper the quality of our result. I will show you. Once the results come, I will show you. So like it is showing now, it is calculating, it is analyzing the transient field. The field that will be radiated by the antenna, it is analyzing that. So after this, what will it do? It will be displayed again. It is saving the results which it has computed till now. There are different monitors, 1D monitor, 2D monitor, 3D monitors. Far field we had selected. We are measuring the results in the far field. So broadband far fields are being evaluated. Different processing steps it is basically showing us. We are almost there. So after far field, it is post processing. That means it is basically preparing the results, calculating far field powers, far field cuts, and done. See, although it is showing that 3 warnings occur, We need not be bothered about that because this solver finished successfully. I hope you can see this term here. Solver finished successfully. Solver finished successfully means that my simulation is over. My simulation is actually complete. Now, where can I see the simulation? See, only one result I will show you because I have included an entirely different session for result analysis. That means the different types of results which we will be obtaining. So, the simulation results, how to interpret the simulation results, that I will discuss separately there. I will just show you one result. See, the first result that we obtain is this S parameters. Under 1D result, I will show you how it looks like. Initially, the navigation tree looks like this. So we started the simulation by right clicking on this field monitor. After this, we obtain the solver finished successfully. That means the simulation is over actually. So the result which will be obtained first, we have to right click or double click on this 1D result. See, 1D results is there. Select it first, then double click. Next is this S parameters. The second option, the S parameters. Select the first option that you have in S parameters, which is S11. The explanation of all these I will give you when I show you the result analysis. Okay. So if you select this S11, now see, the result has been obtained. So frequency is plotted along the horizontal axis and some parameter in dB. So it means some power, whatever. Okay, power level along the y-axis. Now see, this graph is very gradual. I mean, you won't be able to see some step-like features here. This is quite curvy, gradual in nature. Okay. Now, still, if you just zoom in, just try to look carefully here in this region where I am highlighting now. Okay, I will just show you axis markers. In between this region where the marker is now and this region where the marker is now. If you see here, you can see still some steps are there. Just try to observe closely once. Some steps are still there. Now, if I would have selected the number of samples instead of 30 to be 50, then these steps would have become gradual. I mean, you would have got a plain line here like this. See, like this. You would have got a plain line here. So that you can do, that you can optimize, you can increase the number of steps. This effect you will obtain. The computation time will be more, but the graph will be much more gradual. So that is the difference. That is the only difference which we have. So this is the result which we obtain by simulating the patch antenna, the monopole antenna, while incorporating only the Hilbert without using any dielectric block. Next, I will show you how to add this dielectric block to the structure, and then after simulating, what type of result we obtain.